Okay, here's the review for Unit 6, Part 1. The government claims that a student earned a mean of 4,500 during their summer break from studies. Random sample of students gave a sample average of 3,975, and the 95% confidence interval was found to be between 3525 and 4525. Which of the following is the correct interpretation of the 95% confidence interval? So this is, okay, so let's 95% confidence, not the interval, sorry. We're interpreting the confidence level. So this is not, if it's, what's the interpreting the interval? We are 95% confident, the interval from blank to blank contains a true proportion. That's not what this is. This is interpreting the confidence. I'm just going to add the word level there. So we don't even actually have to have the results to be able to interpret this. This is irrelevant, right? It doesn't matter. It's a matter of like reading it, interpreting the level. So what does that mean when we're 95% confident? So let's read A. If the student were to be repeated, if the study were repeated many times, there's a 95% probability that the true average summer earnings is not 45. I don't think that works. I mean, it started out okay, but that it's not 4,500, I don't even understand exactly where that comes from. Because our specific confidence interval does not contain 4,500, there is a 95%, again, so that's not what a confidence level is, interpreting it. If we repeat our survey many times, about 95% of all confidence intervals will contain the value 4,500. So this is tempting. I'm going to keep going because there might be a better one. If we repeat our survey many times, then about 95% of our confidence intervals will contain the true value. This seems perfect. I'm not sure what's wrong with C. There's a 95% probability that the true average earnings will be, no, that's not the confidence level. That's maybe closer to interpreting the interval. Okay, so what did they do wrong in C? If we repeat our survey many times, then about 95% of all confidence intervals will contain the value 4,500. So maybe it's just the true value. So this is not so much about this particular setting. All this information was extraneous, like we didn't really need it. What is a 95% confidence level? So you really don't need any of that information here. We're just talking about the true proportion. What's the chance of that happening if we took many samples and created many intervals? That's what it would be. C was really tempting, I thought. Okay, number 2. Researchers studying the reaction time of drivers state that a 95% confidence interval for the mean time it takes for a driver to apply the brakes after seeing the brake lights on a vehicle in front of us between 1.2 to 1.8 seconds. What are the values of the point estimate? So let's just find that first. That's pretty easy to find in our calculator. So you're just going to average those two numbers, 1.2 plus 1.8. Be sure to get the sum first and then divide that by 2, 1.5. So I know it's one of these guys, right? These are gone. Okay, so margin of error. So what do we need to find margin of error? So the formula is p hat plus or minus the critical value times square root of p times 1 minus p all over n. So this is the margin of error, not this. This is the margin of error, is that formula right there. So we have to find the z critical value for 95%. What I typically do for that is draw 95% in the middle here. So we're trying to find out what the z is right here. If you think about it, if there's 95% in between, there must be 2.5% on each side because it adds up to 100%. So this is 2.5%. So to the left of this, that's how the inverse norm command works. It's going to be 0.975. So if you go to menu 65, I think it's 3, you type in 0.975, it should give us our z-score that we need. which we're going to need to get the margin of error, 1.96. That might be one you memorize just because it's so common. You see it again, lots of 95% confidence intervals. So then P was, I think in this one, let's see, 95 for the mean time it takes drivers to see lights in front of them. The margin of error, we know what the distance is, right? So this is equal to the margin of error. Well, what's the margin of error? If 1.5 is in the middle and it goes plus or minus, like 1.5s are kind of like our p hat here, plus or minus the margin of error to get those two values. So 1.5 plus what is 1.8 or 1.5 minus what? So we know the margin of error is 0.3. Ah, that's nice. So the margin of error is 0.3, so we can set this equation up to equal that. Oh, that's so good. And n, I think do we know n or no? What is the values for, so that, oh, I'm doing all this work. We found the margin of error is basically given to us. It's 0.3. So sorry about that. I was trying to set up, it's like we don't have enough information for this. I was answering a different question about maybe what is n or p if you know one of them. We didn't know either one of those, so but the answer is E, I believe. Okay, well, what I just did might have helped us a little bit, so just more practice on this. So if you want to find the Z critical value, so you want to draw this with 79% inside of here. So I don't know that in my head, so I'm going to do 1 minus 0.79. So there's 21 that's split between these two pieces here, the pieces on each side. So I'm going to divide that by 2. Oops. Divide by 2. So there must be 0.105 on each side. So we want to find this Z critical value. So if I add 0.105 plus 0.79, that's what I'm going to use for my inverse norm here. So 0.895. So I'm going to go menu 653. 0.895 is what we just figured out. And we think it should be 1.25. Well, and 1.253, so 1.25. Oh, it's close. So that should be it. Okay, a noted psychic was tested for ESP. The psychic was presented with 200 cards face down and asked to determine if the card featured one of the 5 symbols: star, cross, circle, square, or 3 wavy lines. The psychic was correct in 48 cases. Okay. I was about to be impressed. I don't know. Might be impressed. It's maybe not terrible. We'll see. If p hat represents the proportion of correct guesses, what is the standard error of p hat? So you might even look on your formula sheet. I think that the difference with standard deviation is a square root of p times 1 minus p over n. I think standard error is the same formula. This is from memory, so hopefully I'm right, times 1 minus p hat. Usually we use this when we don't know the true proportion. If we don't know the true proportion, so we're plugging in p hat here for that guy. So for standard error, so we're going to go square root of, I guess p hat would be 48 out of 200. I guess I could have said 24%. That would have been easier. Times 1 minus, I'm just going to call it 24%, so 1 minus 0.24, all over n, which is 200. So I think this should work. Let's see. So we get square root of a fraction. I'm just going to put 0.24 there, times 0.76, because that's 1 minus that, all over 200. So 0.0302. Oh, another close one. Yeah, I think that's got to be it. So pretty similar to standard deviation there. Forster wants to produce 90% confidence interval for the true proportion of hemlock trees in a forest that are infested with hemlock woolly trees. A serious insect pest. He needs the margin of error to be no more than 0.04. Which of the following equations can be used to find the smallest sample size that will produce for such an interval? So first we've got to figure out the 90% confidence interval. So again, I just like to draw it. So 90%, so 5% must be over here. We want to find this the critical value. So we're going to inverse norm that guy. So menu 653, whoops, menu 653. Area would be 0.95 if you add up those two areas to the left of the Z critical value we want. We get 1.65. So I know it's either this one or this one. These are gone. Okay, so they look pretty similar now. They got the right Z critical value. They have the 0.04. Oh, wait. This one has 0.08. So it's got to be this one, right? Margin of error to be no more than 0.04, because that's the margin of error is the Z critical value times a standard deviation, right? So it's got to be less than 0.04. So it's got to be A. An opinion poll asked a random sample of 100 college seniors how they view their job prospects. In all, 53 say good. Does this poll give convincing evidence to conclude that more than half of all college students think their job prospects are good? P is the true proportion of all college seniors who say their job is good. So, okay, so we have to, are there any like really bad answers? I mean, I'm kind of leaning against these without even pay attention hardly when I was reading. So usually it's equal sign for the null typically, so be shocked if it wasn't, but nothing unusual is happening. Okay, so let's see, 53 say good. So they're trying to prove that more than half of all college students think that. So the alternate is more than half. It's got to be that guy, right? So that's the alternate. It has to be P is greater than 5. You notice these are all, I expected maybe a P hat in here. It's always, nulls and alternate are always the true proportion. So P or mu if you're dealing with means. So to keep that in mind, that could be a good distracting answer. If it has P hat, it's not part of the hypothesis there. So number 7, a test of significance produces a p-value 0.024. What is the correct conclusion? So accept the null. Oh my goodness, that's just craziness. We never accept the null. It's not something we do. So it's not a thing. That's like saying someone's innocent in a court of law. You don't actually say that. You say he's not guilty or guilty. Those are the two options. Reject the null. Let's see. So at the 1% level. So 0.024 is greater than 1. Wait. Yeah, that's greater. That's 2.4% greater. So we don't reject if it's greater. Reject the null at the 5% level. Well, that seems reasonable. I think that's going to be right. Fail to reject at the 5%. No, it's no. So it is D. Okay. The Gallup poll reported that 43% of Americans use the internet for an hour or more each day. You suspect that a greater proportion of students at your school use the internet. You take a random sample of 60 students and find that 36 of them use the internet for an hour or more each day. Assume your school has more than 600 students, so that the conditions are probably going to be met. You will test the hypothesis that the null is 43%. The alternate is, we think it's greater than that. And P is the true proportion of students at school, which is found gives the correct test statistic. So let's see, the null is 0.43, right? So that's the true proportion. So I know we're going to subtract the 0.43 here. Subtract the 0.43. Okay, so I've gotten rid of most of the answers. So 0.6 is the result that we got, right? So that's the same. So do we use the true proportion or do we use the p hat? So this one, just so you know, this one is p and this is the p hat. So typically my rule of thumb is use the true proportion. So I'm pretty sure it's B. Okay, number 9, which of the following statements is true? So these are all about power. Power is something you definitely want to know about. What increases power? That's one of the big topics. So the power of a hypothesis test increases as alpha decreases. Okay, so I just want to think about the chart. This just helps me. This is reject. This is null is true. This is alternate is true. Okay, so this is type 1 error, and this is alpha. It's the type 1 error, and that's alpha. This is the power of the test, and this is type 2, and that's beta, I believe. This 1 minus beta, etc. So the power of a test increases as alpha decreases. So if alpha goes down, that means type 1 goes down, type 2 is going to go up, which means power is going to go down because it's 1 minus beta. So the power of a test increases. Now, power and alpha they're directly varying together, go in the same direction. So that's definitely not it. The power of a test does not depend on the sample size. Well, if you increase the sample size, you increase the power. So I don't think that's true. Power test is equal to the probability of a type 2 error. Type 2 is beta, power is 1 minus beta. That's definitely not true. Power test is measure the ability to test or detect the differences between the estimate value and the true value parameter. I'm leaning heavily towards that answer. I think that's the definition of power, mostly, maybe slightly different than I learned it. As the alpha level increases, so alpha increases, this one increases, the type 2 error increase. No, type 2 goes down. That's the exact opposite, so it's got to be D. I think if you look up the definition of power, it'd be pretty close to that. A radio talk show host with a large audience is interested in the true proportion of adults in his listening area that still read printed newspapers regularly. To find out, he poses the following questions. Do you read a printed newspaper more than 3 days a week? He asks listeners to phone in and respond yes or no. Okay, he asked listeners to phone in and respond yes or no. Of the 100 people, 30 said yes. Which of the following assumptions for inference about a proportion have been violated? Okay, so let's see. So 100 people phoned in. I think that's less than 10% of the population. He has a lot of listeners, so I don't think this is the answer. Well, let's see. NP. So N is 100 times P hat is 0.3, I guess. So that's greater than or equal to 10. And 100 times 0.7, that's greater than or equal to 10. So those seem to be met, so that's not it, because which one has been violated or not met? Yeah, it just says 100 people called in. That's not a random sample, so that's got to be it. An extensive government study conducted this year, a simple random sample of 500 households was selected, of which 80 had experienced property damage due to crime. Calculate and interpret a 99% confidence interval for the true proportion of households that have experienced property damage due to crime. So P is the true proportion of households that have experienced property damage due to crime. You're just parroting back the question there to define the parameter. Start with true proportion and then just parrot it back. Okay, probably a good idea to write a one proportion z interval. Just, that's the thing we're doing here. And so it's a good idea to write that. You want to check the conditions. So random sample. It does say that here. So random sample of 500 households. That'd be even better if you wrote that. Less than 10%. So 80 is less than 10%. Wait, no, sorry. 500, sorry. It's less than 10% of, all households in the US, probably, something like that. It's definitely less than that. You can say that 500 times, what is 80 divided by 500? 16, so 0.16, that's greater than or equal to 10, and 500 times 0.84 has to be greater than or equal to 10, and it certainly is for both. So it checks all the conditions, that's good. P hat, we just did in the calculator, it is 80. It's just a good idea to show it here, is 0.16. And so we want to do the interval here. So it's going to be, we've got to figure out the critical value. Let's just figure it out real quick. So this is 0.99. So that's 0.005, I think, right? So if I go inverse norm here, menu 653, so 0.995, there's only 0.05% off to the right there. So we know that this z-score right here is our z-critical value. It is 2.58, I guess. So let's try to do our interval from scratch. So it would be 0.16 plus or minus 2.58 times the standard deviation, which is so 0.16 times 0.84 over n, which is 500. So for fun, we're going to do this in our calculator and see if we get a reasonable answer. So 0.16 plus 2.58. I say that because we could just do the whole thing in our calculator, which we'll do in a second. Square root of 0.16 times 0.84 all over 500. Copy and paste that, change the plus to a minus. So we think those are the lower bound and upper bound, so 0.117877, comma 0.20, I'm just going to round that to 23, I think. Okay, so we think that's our interval here. We showed the work, it's pretty good there. Let's just do it, the whole thing in our calculator. So menu 6, so this is an interval, so I'm going to go to intervals and it's called a 1 prop z interval. The numbers, this is an easy one to do in your calculator for the most part, so it's 80 out of 500, and this was 0.99, I believe. So we got from 0.11, so we got the same thing, didn't we? Even gives you p hat. So the two numbers you have to have listed here, and it's okay to list them in the formula, is, let's see, you've got to have the, well, you've got to have the lower bound and upper bound. And p hat, I think you should have p hat. I would list that. It's enough work to show, believe it or not, for the do section of this one. So finally, we want to say in words, we are 99% confident the interval from there to there, like blank to blank, contains the true proportion of households that have experienced property damage due to crime. So that's the interpretation of the interval, the conclusion there. Last year, it was found that the proportion of households that had been damaged due to crime was 18%. So the big thing you're looking for is that in the interval or not, 0.18. So 0.18 is in the interval. Based on this interval, is there convincing evidence? No, we don't think there is convincing evidence because 18% is in the interval. It's a reasonable value. It's what was it called? A plausible value. So we don't think that unusual, and so we don't have enough evidence to say that it is decreased from the 18%. Just want to show you what they wrote here, their answer. Let's see if they did anything different. Yeah, it all looks good. Okay, let's do the test now. So Mark, a starting player for a major college basketball team, made only 40% of his free throws last season. That's bad, by the way. During the summer, he worked in developing a softer shot in hopes of improving his free throw percentage. To gauge his current ability, Mark attempts 40 free throws. He makes 25 of them and misses 15 shots. He makes 25 of the shots and misses 15. Okay, that was a weird way to say it. Assume that these free throw attempts are a random sample from the population of all possible shots he can take. Is there convincing evidence at the 1% significance level that Mark's free throw ability has improved? Wow, 1%. They're getting strict on this one, right? So what is this called? This is called a one-prop z-test. And P, define the parameter. P is the true proportion of free throws made during the summer, I think. Okay, so we check the sample, so random sample. So random sample, it said to consider it a random sample. So we're saying check it. It said that in there. Remember that, random sample. Okay, less than 10%. 40 times, this one could be tight. Let's see, maybe not. So times 0.4, I believe, should be greater than 10. Well, that's true. And then 40 times 0.6 should also be greater than or equal to 10. So it checks the conditions, which is nice. Okay, so what do we have to do next? Do we want to do, z equals, so this is going to be minus 0.4, right? We probably should find out the p hat. So p hat is, let's see, 25 out of 40. So we might need to type that in our calculator. 25 divided by 40. So that's 0.625. So 0.625, wow, maybe it has improved. Minus 0.4 over the square root of 40. So I think this would be 0.4 times 0.6. And we're going to type that in our calculator and get the z-score. So 0.625 minus 0.4 over square root of 0.4 times 0.6 all over 40. So we think this is 2.9. Well, that's pretty significant. It's more than 2 standard deviation away, almost 3. So I'm thinking this is going to be a pretty small p-value, right? So you kind of draw it, that's 0, 1, 2, 3. Somewhere in here, we're shading to the right. This is a very small area. So how small is it? Well, we could do norm CDF for this guy, right? So menu 652. We're going to go from 2.905 to infinity. 0 and 1 are default because it's these scores. So the p-value we think is 0.001836. That's pretty small. So let's do the whole test in our calculator just to make sure we did everything right. So menu 6, this is a test, so it goes number 7 and 1 prop z test. So the null is 0.4. Our thing we did was 25, whoops, 25 out of 40 is what I meant to say. 25, oh, I'm glad I did this because I didn't think about the fact that I should do the alternate and null. I did not do that. So the null, we should have started with this. That would be good. Put colons after that. So p equals 0.4. And the alternate, let's see what the direction would be. He hopes on improving, so we think it's going to be greater than 0.4. Wow, I should have done that first. Sorry about that. Did things out of order. Greater than, we're going to say okay. And we get 0.0018. That's perfect. That's what we got here. The numbers you have to have is z, that's z, and p-value. Those are the two numbers you have to have. Do this. Now we can make our conclusion. So you want to start with because our p-value of 0.0018 is less than our alpha level of 0.01. We reject the null. We reject the null. We have evidence. We do reject. We do have evidence that his free throw shooting over the summer has improved. Something to that effect. Interpret the p-value of 0.0018. So you want to start with assuming the null is true. In other words, assuming that his true percentage of free throw shooting is 40%, the chance or the probability of getting a result as extreme as we got, I forgot what it was, but 0.625, or more extreme is 0.0018. Let's see what they wrote for those two, just so you have the answers. So assuming that Mark's free throw ability currently is the same as that of last season. Oh, that was last season. I didn't read that carefully. That Mark will still shoot a 40% free throw. There's a 0.0019 probability of getting a sample portion of 0.625 or greater just by chance in a random sample of 40 free throws. We have convincing evidence that the population of all free throw shots is greater than 40%. Yeah. So I just checking some of the things we did there. Good. That's the end of the review.